Head toward the center of our galaxy, and you're walking into a war zone of radiation that would shred your DNA in minutes. There isn't just one habitable zone. Astronomers have mapped at least 6 of them, and most of the galaxy fails every single one. One of those 6 could keep a planet alive for trillions of years, longer than the sun will ever manage for Earth. We're climbing through every one of them, in order of how strange they get, until we find out which zone actually wins. Start with the one you already know, the classic habitable zone, the strip around a star where liquid water can exist on a surface. So why isn't every planet inside that strip actually alive? Venus sits just inside its inner edge, and its oceans didn't just evaporate. They triggered a runaway greenhouse that never switched off. Mars sits just outside the outer edge, air too thin to hold heat, whatever water it had now frozen into the ground. Both are technically in the neighborhood, neither one works. Earth is the only one of the 3 that landed inside the narrow band between them. 2 planets missed, 1 planet didn't. That's a worse hit rate than it sounds. Habitable zone is 1 line on a star map. It's at least 6 zones, and they can contradict each other. And that's before you even ask whether the galaxy itself will let you live there at all. Your galactic address matters just as much as your solar one. Welcome to the galactic habitable zone. Too close to the core, and you're bathed in the kind of radiation and supernova crossfire that can sterilize a planet outright. Spiral arms drag stars through crowded, unstable regions thick with radiation and gravitational chaos. Slip through one of those arms at the wrong moment, and stability itself becomes the rarest resource in the galaxy. Too far out toward the rim, and there simply isn't enough leftover heavy material to build rocky planets at all. Remember that radiation storm from the opening. That's the exact danger drawing the galactic zone's inner edge. Our sun sits in a surprisingly quiet ring between the 2 extremes. Not the graveyard, not the wasteland, just fine. Get that address wrong, and none of the other zones even matter. There's no planet left to ask the question about. So location is the easy filter. The next zone doesn't care where your star is. It cares whether your planet can even turn. This is the zone from the very first line of this video. Planets locked so tightly to dim stars that one face never turns away. One side bakes under permanent daylight, the other freezes under permanent night. There is no such thing as sunset there. Somewhere between those 2 hells sits a thin ring of twilight, the only strip temperate enough to maybe survive in. Strong enough winds might carry warm air around to the frozen side before it can freeze out completely. We've already found real candidates for worlds like this, locked in tight around dim stars like Proxima Centauri and TRAPPIST-1. Nobody has confirmed the warm air theory actually works on a real planet yet. It's a hopeful model, not a measurement. There's a catch. The dim stars these planets orbit are also the ones most likely to blast them with flares. A hard enough flare can strip a thin atmosphere away completely, and without air, that twilight ring stops mattering. And even a planet that survives the locking and the flare still isn't done. The zone underneath it keeps moving. As a star ages, its habitable zone physically moves, sliding outward like a slow-motion eviction notice. Our sun is roughly halfway through that slide, slowly brightening year after year, for billions of years running. One day the classic habitable zone will move past Earth entirely, and Earth won't leave it by getting colder. Roughly 1 billion years from now, Earth gets cooked out of the zone, not frozen out of it. Later the sun swells into a red giant, and the zone doesn't just move, it leaps outward past Earth's orbit entirely. For a while the zone parks itself out around Jupiter's icy moons, worlds that were never supposed to be habitable. Every planet with a star is riding a habitable zone that never actually stops sliding underneath it. Then the swelling stops, the star collapses down to its core, and the zone doesn't disappear, it just gets stranger. A white dwarf is a dead star's leftover core, Earth-sized. No fusion left, just fading heat drifting into space. That fading heat is stable enough to host its own tiny habitable zone, just packed in absurdly close. A planet would have to orbit closer than Mercury does to our sun, just to stay warm enough for liquid water. That closeness comes at a price. Tidal forces this extreme would almost certainly lock the planet, same as before. But a white dwarf cools so slowly that this tiny zone can stay stable for billions of years after the star that made it already died. Which means the last habitable real estate around a star like our sun might not exist while the sun is even still shining. It might only switch on after the sun is already dead. Real estate that only opens after the seller is deceased. Space has a strange sense of timing. Compare that patient afterlife to a star that never rushes toward dying in the first place. Red dwarfs are the boring, small, dim stars nobody names their kid after, and they're also the longest-lived stars in the universe. A star like our sun burns for about 10 billion years. A red dwarf can keep burning for trillions. Their habitable zones sit in tight and barely move, stable for longer than the universe has even existed so far. There's a catch. Young red dwarfs are also the most violently unstable stars we know, flaring hard enough to strip an atmosphere clean off. And because that zone sits so close in, almost every planet inside it ends up tidally locked, the same knife-edge twilight from before. It's also why so many current searches for life point straight at red dwarfs, not stars like our own. But if a planet survives that violent youth, the flares calm down, and the star settles into billions, then trillions of quiet years. No star like our sun will ever offer that kind of runway. A red dwarf could keep a planet habitable long after every sun-like star in the observable universe has already burned out and died. Here's the pattern hiding underneath all 6 of these zones. None of them are really about finding the right neighborhood. Every one of them is the same fight. Can a planet balance the energy it receives against the energy it loses, wherever that happens? The classic zone is that fight over light. The galactic zone is that fight over radiation. The tidal zone is that fight over rotation. The shifting zone, the white dwarf zone, and the red dwarf zone play out that same fight across billions or trillions of years, instead of minutes. Once you see it that way, the real question was never where. It was always how long. So which zone actually wins on how long? Not the classic zone. Earth's own window is finite and already about half spent. Not the white dwarf zone either, beautiful, but it only opens for business after a star has already finished dying. It's the red dwarf habitable zone. A planet locked in tight around one of these small, patient stars could stay habitable for trillions of years, outliving every habitable window the sun will ever give Earth combined. That's not a consolation prize. That's the single longest-lasting real estate for life that physics currently allows. And it was sitting there the whole time, orbiting the star everyone always overlooks. It means the most durable home for life in the universe probably isn't a bright yellow star like ours. It's the small, dim ones we usually ignore. Earth's habitable window is a genuine stroke of luck, running for a few billion years on a star that won't stay stable forever. If red dwarfs can outlast every star like the sun, the obvious next question is what happens to a planet once its own star finally dies. That's next on Cosmic Scale, every way a star's death reshapes the planets it leaves behind. Subscribe, because the universe keeps finding new ways to almost let life exist.